everyone. So today we are here to for the PhD defense of Mrs. Zineb ZIANI, titled Artificial Intelligence and HPC Convergence for Enhanced Anomaly Detection. This work was achieved in the context of a collaboration between the University of Paris-Saclay and Numerics Technology under the supervision of Professor Naïd Emad from the University of Saclay, Paris-Saclay, and Monder Ayadi, je trouve.
Numerics. Ouais, pas besoin de
Voilà. CEO of Numerics. The members of the PhD panel are two examiners, two reviewers, Professor Eric Dar from the University of Stanford and Professor Noureddin Melad from the University of Lille, and four examiners, Professor Fabienne Jezekiel from professor at the University of Maître de Conférence. Lecturer at Paris Panthéon-Assas. Exactly. Dr. France Boileau-Cerneux from CEA. Dr. Martial Mansip from
Maison de la simulation.
Maison de la Simulation, and myself, Professor Soraya Zerta from University of Saclay. So you have 45 minutes to present your work.
Great, thank you. So, hello everyone. Thank you for being here today. It's a pleasure and an honor to present my PhD today, thesis. So I'm gonna present my research on the convergence of AI and HPC for enhanced anomaly detection. So this thesis is a collaborative project research between the University of Paris-Saclay and Numerics Company. My thesis supervisor is Professor Naïd Emad, and my industrial supervisor is Dr. Monder Ayadi. And the hosting laboratories are Maison de la Simulation and SDPA. So in the construction or in the this thesis, we will start by an introduction. Then we will move to a statistical art, the approach and methodology. Then the proposed anomaly detection framework, a computing context, a performance evaluation, and finally a conclusion. So in the introduction, we are going to start talking about the context of AI and HPC convergence, then defining anomaly detection, and what's an effective anomaly detection. So artificial intelligence, or AI, refers to the ability of machines to replicate human cognitive processes such as learning, reasoning, and decision making. So this is achieved through sophisticated algorithms and mathematical models that actually learn from data to make predictions or solve problems. HPC, or high performance, on the other hand, process data and actually perform calculations at speeds that far exceed those of conventional computers. So HPC is optimized actually for handling computationally demanded tasks, such as large-scale mathematical operations. So now, when AI and HPC converge, they unlock transformative possibilities. The immense processing power from HPC enables AI for efficient detection and efficient actually processing models. So enabling advanced solutions such as highly effective anomaly detection. So what's anomaly detection? Anomaly detection is the process of identifying events or patterns that deviate from what is expected or considered normal in a given system or dataset. It's a versatile technique that can be used in different fields for different purposes, such as disease detection in healthcare, fraud detection in finance, intrusion detection in cybersecurity, and fault detection in manufacturing. So actually, by detecting anomalies, we boost safety, improve effectiveness, manage risks, and also ensure quality. This is why it's a must-have in every system. So To truly or understand how we measure the effectiveness of an anomaly detection system, we actually evaluate them against several cases or several criteria case, such as the correctness of detection, which means the accuracy, the precision of this detection, also the robustness against noise and inconsistencies, the scalability handling large-scale data sets, also the detection time or the speed of detection, also the generalization with unseen data sets or unseen tests for tests, and also interpretability for results, and finally the adaptability to adjust the models for dynamic data. So to I'm going to say create an effective solution. The convergence of these elements, reliable detection, fast detection, and scalable detection must be achieved. And this is our goal in this paper. So now we are going to move to state of the art, where we are going to talk about the evolution of anomaly detection, actually the history and methods used, also the HPC-driven improvements, and finally the challenges in anomaly detection that we will try to face. So, anomaly detection has come a long way, evolving alongside advancements in technology and also data um, data analysis techniques. So to truly appreciate the solutions we have today, we have to look back at how this field has developed over time. So we are going to start with the 1800s with statistical methods where the mean, like for example, the mean variance hypothesis founding the or forming the foundation. Moving to the 1960s, where traditional machine learning models like the Kainer's neighbor, clustering, and linear regression has emerged, to 2000 with deep learning that actually introduced advanced methods for anomaly detection like the autoencoders and GANs, to the 2010 where we had the combination of hybrid methods with actually real-time approaches, and finally last years or in the recent years we had the HPC starting to enhance deep learning applications for anomaly detection. So to have a look a little bit closer to these methods, after the statistical methods, we had the machine learning models that actually learn or made models learning with several learning methods, such as supervised, where actually models are trained using labeled data to actually predict data points and flag deviation. Also, we have unsupervised methods, and these methods use unlabeled data to find anomalies. We can take, for example, the clustering with the k-means, and semi-supervised methods that combine actually a small amount of labeled data with a large amount of unlabeled data, and we can have, as an example, the co-training. So next, we have actually deep learning also in the context of anomaly detection. It introduced ideas, important ideas for detecting anomalies, and two main approaches, interesting approaches, are reconstruction-based methods, where actually errors are computed from rebuilt data to actually find unusual patterns like autoencoders. And also we have generative models where actually we compare data or real data from fake data generated by models like GANs to actually spot differences. Also, after deep learning, we had, as I said earlier, the combination of hybrid approaches and the need to real-time approaches to detect immediate anomalies that actually merged also, where hybrid approaches combine several approaches actually to leverage strengths of some models and also face the weaknesses of them. And we have we can have an example such as actually Quad. It's a combined anomaly detection framework. And we have also real-time approaches that actually continuously monitor and process stream data in real time to detect immediate anomalies. And we can take, for example, Apache Kafka. So now we are going to move to graph data and methods. So graph transformation involves, or in the context of anomaly detection, involves converting a data set such as logs or tabular data into a graph structure where nodes represent individual data points and each actually represents the interaction or the communications between these nodes. So they this graph transformation can be done with several methods, and we can take, for example, the k-nearest neighbor that do that and transform or convert a table into a graph. So we have also graph neural networks. Graph neural networks are a deep learning approach or models that process graph structured data by aggregating node futures, and also neighbor information through this convolutions. We can take, for example, the graph convolutional GTNs, graph convolutional network. So now we are going to talk about HPC and what does it bring to anomaly detection, and specifically here we are going to talk about deep learning. So we had actually around 2010 and 2012 an explosion of data that are raised because of social media. We can take, for example, photos, images, posts, and documents. But actually, this deep learning was constrained by the lack of labeled data or enough and sufficient labeled data to and also scalable algorithms to train these models. So handling these large amounts of data and complex computation required complex machines, or I'm going to say powerful machines. So here, HPC combined with GPUs, graphic processing units, became essential to handle these large amounts of data. So in 2012, we had actually a breakdown. We're gonna say of deep learning method or model leveraging GPUs, which is AlexNet to win the ImageNet competition, which actually demonstrated the power of parallel computing to train deep learning models, and this was the beginning of a rapid advancement in artificial intelligence. So when we talk about HPC, basically we talk about resources, but this is not what we want here. Actually, to improve anomaly detection with HPC, we need to change how we think about anomaly detection, and also about the way we design anomaly detection. So instead of following traditional step-by-step models or sequential models, we need to to use, as I said, HPC as more than just a resources, and think about how to divide the models into sequences and made the anomaly detection models parallel. So reframing anomaly detection with parallel thinking is essential for I'm gonna say taking the natural intrinsic parallelism in models, and also it makes better use of resources instead of just using them, speeds up analysis, and also enhances scalability. So when we talk about anomaly detection, we talk about data nature, we talk about a lot of or several challenges. So here we will start about big data and immense volumes of data that we have, how to handle them, the nature of data, structured, unstructured, semi-structured, and also the velocity of training them or processing them. Also, we talk about data nature, and we talk here about imbalanced data, balanced data, dynamic data that change with time. Like, for example, attacks. We have sophisticated attacks in cybersecurity that change the behavior, and it's very hard to detect them. So this is a very big challenge in anomaly detection. And also the processing of data, how we clean the data, handle the missing values, selecting the good features for a good detection. And finally, we have anomaly detection methods adapted for big data is actually a challenge also, because they lack of good scalability, efficiency, and also distributed computing and real-time detection. So after having an idea about the state of the bargain or the current state of the art current solution, we are going to talk about the approach and methodology used. So we are going to start talking about ensemble learning, also unite and conquer approach, and usage framework that combine unite and conquer. So here we are going to start talking about bagging. What's bagging? Bagging is a method of ensemble learning. Ensemble learning is ensemble learning is a machine learning technique that combines several methods to improve their efficiency and improve the results for better detection. So bagging, we are going to start with bagging. Bagging, instead of taking the whole data set and train the model on the whole data set, it splits the data on several bags that could be run in parallel and also create copies of the models. This is a simple way, but we can also use different models where each model is trained on a part of data, as we can see here, that we have a sampling of the bags, and then each copy of models or each model is trained in a part of data. At the end, we will have predictions or results from all the bags for all the methods, and then we will do an aggregation to choose a final prediction. So bagging actually is used to prevent overfitting, because sometimes when we train a model with a big, large amounts of data, we can suffer from overfitting, reason why we use bagging in this case to prevent overfitting. Next, we have boosting, which is also a method of ensemble learning. And this time, it's actually, I'm going to say the inverse of bagging, because instead of splitting the data set here, we train basically several weak learners on the whole data set. So we will give the whole data set to the first weak learner or model that will take the whole data set, will be trained on it, will give predictions, and then it will boost the next method with the misclassified data of the previous one. And like this, till we continue all the methods, each one will boost the others. And at the end, we will have also an aggregation to choose the final one, the best one. Now we are going to stack. So, but what I didn't say about, um, sorry, what I didn't say about boosting is that boosting is the inverse. It's to actually prevent underfitting. Because as I said, we actually train weak learners, so they the boosting improves the efficiency and it prevents underfitting. So we are moving to see stacking, which is also an ensemble learning technique. Actually, here we will have our methods. Let's suppose we are doing a bagging or boosting or whatever. We have models that are trained on data, and we have some predictions. But now, instead of doing an aggregation, a basic aggregation, which is choosing the maximum or an average, here we are going to take this prediction as an input for another model, and then we will have a model which is trained on this input, and it will give us an output. So actually, it just changed the aggregation that we choose basically, which is basically just a mean or a variance or whatever. Now we are going to see unite and conquer, which is a method or an approach initially used for linear algebra. It involves several co-methods or iterative co-methods collaborating together to for solving the same problem to improve the results. So we will have actually here the first co-method, for example, saving the, the, the same problem, and co-method two saving also the same problem, and the third one. So they will communicate at the end of each iteration, and they will improve the initial condition thanks to this function, which is the restarting function, choosing a good, better restarting condition instead of the initial conditions, thanks to the sharing communication between all of them. So actually, it's kind of boosting also over iteration. So we are going to say unite and conquer fundamental principles. So one of the important case of unite and conquer is the multi-level parallelism. We can actually use the multi-level parallelism using unite and conquer. Also the fault tolerance. If one of them is not working, others can continue working without any problem and sharing the information to improve the results until the convergence. Also, it works with synchronous and also asynchronous communications and the heterogeneity of campaigns, so we can combine different chromatids, and finally the load balancing, and we have more actually more than 5 advantages of Unite and Conquer. Now, when we combine Unite and Conquer to Ensemble learning, we have some similarities between Unite and Conquer and Ensemble learning, as we said in previous slide. We can see that first of all, both of them use chromatids, and in boosting and bagging and stacking also it uses co-models, so it's the same principle. Also, boosting is iterative, like Unite and Conquer, which is by nature iterative. It repeats the same thing until the convergence. And also, bagging, which is parallel, and Unite Conquer also it has multi-level parallelism. About the approach of Unite and Conquer, since we are seeing that they have similarities, what actually Unite and Conquer bring to Ensemble learning? Unite and Conquer, instead of defining a number of iterations that we will continue, like with Ensemble learning, actually we have to define a number of iterations. It's not actually done with Unite and Conquer because it's continue until the convergence, while improving the initial conditions. And also, this is a good point, improving the initial conditions, because bagging and boosting doesn't improve the initial conditions. So, Unite and Conquer combined with bagging and learning was already seen in your PhD thesis in 2021. And here we propose a generalized approach and also with a parallelized and scalable approach. So now, after seeing some methods that we will use, we are going to propose our frameworks, which are frameworks for anomaly detection, which are UC2B, and we have several variants. So we are going to start with the first variant. So we can see here that we have models, and each one, like they are sequential. We have the first one, second one, and third one. So this is UC2B sequential, the first version. So it takes the data set, it gives it to all the chromatids or models, and then inside of the chromatid or the co-model, here we are talking about machine learning models. So inside of it, we will have a bagging where actually instead of training the whole data set, the model one on the whole data set, we split the dataset into bag and we create copies, and each copy is trained on a bag. Then, when it will finish, it will boost the second one by giving the misclassified instances. These misclassified instances will be used in model 2 with higher weight. So it will be boosted by the previous one. And same for model 3. And then after this, we will have a synchronization to check if we achieve the satisfactory accuracy that we want. If we had the satisfactory accuracy, if not, we will have the false positive and false negative instances that will be given to the dataset with a higher weight again for a boost. And this is the role of Unite and Conquer. This is done, this restarting condition is done thanks to this function that we use that I can explain later if you want. So this is the function we have made to improve or to boost the instances. So as we can see here, we have first of all double boosting, because we have a boosting which is here inside the chromatids, and also after the whole framework, after the whole iteration. And also we have an update conditions thanks to this function of the restarting function, and which actually design the second boost. Now we are going to present UC2B in parallel with synchronous communications. So we will not have the insider boost anymore. We will have chromatids that run in parallel, and inside of each one, we will have a double parallelism where we will have bags and copies of this method which are trained on it. So the same process at the end, we will have a synchronization to check if we achieved the wanted accuracy, and then the positive and false negative instances will be reinjected or will have a higher weight in the data set for the next iteration. So it's the same, I'm going to say, version, but the other one, the previous one was in sequential, and this one is in parallel. And after that, we will have an aggregation that will be stacking. So we can either choose the maximum or a mean or whatever, or train another model to choose the best one. And we will have a final predictions if the satisfactory accuracy is achieved. So here, what we have actually, we have gained the fault tolerance, because here the commands are not dependent. So if one of them doesn't work, it's not gonna impact the whole process or the whole framework. So now we are going to see UC2B variant, but with asynchronous communications. What what are we meaning by asynchronous communications? When we talk about asynchronous communications, it means that we will not have a synchronization at the end of all of them. They will communicate, but for example, let's suppose that I have model A that finished before all of them. It's not gonna wait for all of them to give its result to improve the restarting conditions to start. It will boost itself and start another iteration. And this one, when it will finish, it will receive the results of the first one and then continue. So this is what we call, or what we mean about asynchronous communications. So the same process, we will check if the satisfactory accuracy is achieved. If not, we will start another iteration. So here we have also the boost with the restarting function, and also we have the fault tolerance, and also we have the asynchronism, which actually accelerate the convergence and also the detection time. Finally, we have this variant, which is multi-parallel asynchronism, and if you can say, we added data parallelism in addition to the parallelism that we have inside methods and the parallelism of methods. Let's suppose we have actually true commands. We have three methods and we have three nodes. This one's going to be trained on a node, this one on a node, and this one on a node. And we want to use more nodes. That in this case, what are we going to do? We are going to take the whole data set and split it into bags, like as we can say, data 1, data 2, and data 3. And this command or this commodel will be trained on data 1 on a node, on data 2 on another node, on a data 3 on another node. Same for model B. It's going to be trained on another node on the data 1, on another node on data 2, and on another node on data 3, which means that if we have 3 commands, we will use 9 nodes because we have 3 big bags. So it's kind of bagging, but it's actually outside instead of being inside. So here we have also, we are seeing the multi-level parallelism, and in addition to the asynchronous communications always. So if, for example, I have one of them which is longer or takes time to train, others will not wait for it. They will continue and share communications or share results between them to choose better starting conditions for the next iterations, and they will continue until the convergence. And at the end, we will choose aggregation or stacking depending on the results or what we want, or also the domain application. So now we are going to talk about the computing context. So we are going to talk about our target application. We are going also to present the data used and the high performance architectures. So our targeted application is cybersecurity, because we are working with numerics company, and I work in numerics company, where we want to enhance the SWAR. SWAR stands for Security Automation and Orchestration Automation Instead. It's a platform that detects anomalies in cybersecurity. So it detects attacks. So what we want to do, or the aim of the company to do, is to, like, we will have a SWAR that we will receive the flux of information or logs in the real time, and then we will have a supercomputer or a cluster where we will have our machine learning models and our frameworks that we will detect anomalies in the same time. So what we mean by this is that we are looking for a continued training methods and not actually for models or a framework that will continue in offline or will be trained in offline. It's a continued training models, which means that the execution time is important for us. Why are we looking for this, and what's the aim of this? In domains like cybersecurity, as I said, attacks are sophisticated. They change the behavior, they are dynamic. So when we will, or when a new attack will infest the machine, we will not know it if we haven't seen it before. Reason why we need actually a continued training framework. So this combination or the collaboration of a SWAR with a supercomputer or a cluster, which will allow us to have a rapid report of attack if we have. So next we are talking about the data set used. The data set used is UNSW AP15. It's actually a network IDS base created at UNSW University. It captures traffic in a controlled environment with various operation systems, applications, and also attacks, where the attacks come from more than 10 malware families. And it's labeled as a normal and attack. It contains almost 2.6 million records that was done over 30 days. And as we can see, it's an imbalanced data set with 49 futures. So here we are going to say the hardware specifications used. So we used Rouge. We used the Rouge cluster at the Rouge cluster at the Paris-Saclay Mesocentre, and Riken Fugaku supercomputer ranked top one in 2021 and 2020 also in the world, and top one since 2022 for iterated methods in the world. And so we can see that actually our framework was challenged, or our frameworks were challenged with hybrid architectures and in different environments. So now we are going to talk about the implementation and also the evaluation, how we implemented our framework, and we will evaluate it. Actually, to evaluate our framework, we have two specific or main goals. The first one is to validate the approach to see if it detects the anomalies, if it detects very well, it's accurate from detection, and then we have also to check the calculation efficiency. So for that, we use different metrics. So we are going to start about the parallel programming model. Our parallel programming model is based in two main approaches. The first one is campaign approach. Actually, a campaign-based approach, in this campaign, each function is considered a campaign. So it allows interoperability, also realizability, and also durability. And also we have the second K, which is graph campaign attack. Here the application is structured as a graph campaign where each command or each command in our case is considered a campaign. So each campaign can be a graph of task. So it could be actually, or each one could be in a processor or on a card using multi-threading optimization. Here we are going to see the mapping of our implementation of Fugaku. So here we can see A64FX node design where a comatal is trained. So here we will have a comatal is trained. And here we have the cores. We have 48 cores in the total. And for us, we use 10 bags, then we use 10 cores. So each model is trained in a node, as I said. So here it represents a model or command. And asynchronous communications are interchromatic, and also we have data parallelism intracomatic inside the model. So to evaluate our framework, we use the accuracy, precision, recall, and F1 score. Before starting the final accuracy, precision, recall, and F1 score, we need to understand what false positive, false negative, and true positive and true negative. Actually, true positives are cases where the actual data is positive and correctly predicted as positive. False negative is when actually the predicted or the real label um, is positive, but it was labeled as negative. False positive is when actually it was predicted as a positive, but it was negative. And true negative is when actually the correct label is negative and it was correctly predicted as negative. So what is the accuracy? The accuracy is the ratio of correctly classified instances to the total number of instances in the data set. Precision is the ratio of true positive predictions to all predicted positive. Recall is the ratio of true positive predictions to all actual positive in the dataset. And the F1 score is the mean of prediction, precision, and recall. So to present the results, we are going to start by, as I said, validating the approach with the accuracy, F1 score, and the detection rate. So we are going to start by evaluating the sequential UC2B. So we have here the convergence of serial UC2B. In our experiment, we used three methods: random forest, supervector machine, and iForest. These methods are band and boost inside because we shouldn't forget that this one is double boost, is the sequential version. So we have actually iForest, SVC, and then random forest. Random forest gives a very good result because it was the last one, which means that it was boosted by iForest, SVC, and then random forest. The red plot is the ensemble of all of them. And finally, we have unite and conquer, which is the best of all of them, which gives better accuracy and results of all of them. Here we have the F1 score, where we added actually some comatids to see how it will behave with more comatids. So we can see actually that something important, that iForest has 0% F1 score, which means that it wasn't capable of detecting anomalies. It was just detecting I'm gonna say the majority class, which is normal data sets, or normal instances, because as we said, we have seen that the data set is unlabeled or unbalanced. And we can see also that actually we had a good F1 score results, also for random forest, which is the blue. It has very good accuracy and also very high F1 score. And as I said, it's because it was boosted with all of them before. And we have actually Unite and Conquer UC2B, Unite and Conquer Train and Test, which achieved a good accuracy and which has a higher score. And actually, the similarity, or I'm going to say the nearest value on the train to the test means that we don't suffer from overfit. So here we are going to present UC2B in parallel, so the version in parallel. As it was expected, since we have the comatids or co-models that are in parallel and we don't have anymore the insider boosting, we haven't anymore the same accuracy. In the previous one, we had 99.5 on test accuracy, but here it's like 97%. So we a little bit lose 2% accuracy, and this is because we don't have the insider boost anymore. So to try to solve this problem or to see what we can do about this, we increase the number of comatids. So here we had 4 comatids, and we doubled them to 8 to see how it will behave. Are we going to have the same accuracy? So we have seen that increasing the number of comatids improves the results and improves the accuracy. So we can see here that it achieved 99.5 almost, or 4 with 8 comatids, which means that heterogeneity of compounds, the heterogeneity of co-models, and the increasing the number of chromates improves the accuracy. So here we can see the results actually. Yeah, it's here. So as we increase the number of chromates, we also want to see closer the impact of chromates. So here we can see the accuracy achieved with 4, with 6, and with 8 chromates, which means increasing the number of chromates improves the accuracy. And here we can see the difference that we had in train and test. We should not forget that it's like not even 1% difference between them, which means that the results are this. So now we are going to see unite and conquer in parallel with synchronous communications. So we can see that regarding the accuracy, it's actually a very good accuracy and very high accuracy on train and test datasets. So here we want to see the impact of the function of restarting conditions, where we improve the restarting conditions. We can see here that actually in the first iteration, we had 7,000 instances or misclassified instances. After this actually iteration, it went to 4,000, 3,400. And this is achieved with the restarting condition function that improve actually the results by increasing the number, increasing the weight of instances. And here we can see the confidence score, where we use actually the function 1, that's the absolute value between train and test, to actually evaluate the confidence score. Here, just to give you an idea about all of the metrics used, so we can see that actually UCGB or parallel UCGB remains the best between all of them, achieving high accuracy and high F1 score, high recall, and also a confidence score. So now we also try out our framework with graph neural networks, so with GCNs. So, and here we used stacking, and in the stacking we used actually MLP. So we can see that always actually the unite and conquer with bagging and boosting remains the best, which is actually the MLP one with stacking. So this one represents UCGB. Now we are going actually to evaluate the efficiency of our computation efficiency of our framework. We will actually evaluate scalability with strong and weak scalability. We are going to start talking about our sequential actually UCGB. We need to say that first of all, since it was trained on one node, so we don't have scalability figures, but it took actually 10 days or over a little bit over 10 days to be trained on one node for the whole framework. But now we are going to present the parallel version, the first parallel version, and we can see here the speed up or the execution time, the increase in execution time, and this, I have to say that this is the synchronous version. So we can see that when we increase the number of commits, and also when we choose actually models that takes time, it increases the number of the time, the execution time, which means that we have to choose slightly actually with attention our commits. Now we are going to compare the synchronous to the asynchronous commits, and here we are talking about the accuracy stability. So basically, when we talk about parallelizing models on AI or on machine learning, we lose actually accuracy when we divide the data or the models across models. So this is what we did here. We went from 4 nodes to 40 nodes, and we want to see if we will change or we will lose in detection rate from 4 to 40, and we see that we didn't really lose something important. So from 99.8% to 99.73, and also for the F1 score the same. This F1 score accuracy here. So for the precision, sorry, we went from 97.8 to 97.75. So here we are going to compare the scalability. So we are going to compare the strong scalability of both versions and of both versions here. So we're going to start by the strong scalability. So we can see that here we have the synchronous communications and we have the asynchronous communication. The asynchronous communications actually we have a speed of 3 times, so it's not something important, but we can see that it's more adapted to weak scale. So we can see that with synchronous communications, actually an ideal scalability should be a flat curve, but actually with the asynchronous version, it is actually adapted to weak scale. So to improve this, we went to graph and to check how the speed up will behave. So we went to 512 nodes on Fugaku, and actually we can see that speed up is over 52 times, which means that we handled the large scale with the version of stacking with actually graph neural networks where we use GCX. So to conclude, we actually validate the approach with 99.5 accuracy detection and also a fast detection because we went from 10 days, it's not a comparison, it's not the same computer, but we reduced the execution time to 15 seconds, and we are talking about the execution time from the training to detection. And also we have a scalable detection, we have version which is actually more adapted to weak scale, and also another one which is more adapted to strong scale. So to conclude, we actually combined an innovative integration of machine learning models inspired by Unite and Conquer approach. Also, the heterogeneity of contents, it plays a crucial role in our framework. Also, the multi-level parallelism and natural cross brain in our framework, in our methodology. So our future work, we propose to an extension to spectral methods, since it's like Unite and Conquer, which is for linear algebra. Also, integration with federated learning for more privacy, for like actually domains like cybersecurity, and also generalization to border domain, and also to make in production the product in numerics, and also to try it on different domains and other domains. So in this thesis, or in collaboration with this thesis, we had, or I had two stays in Riken, one in Kobe to work on Fugaku, another one in Tokyo also to work on Fugaku with AI team, and the first one with the programming environment team. And actually, this leads to some publications with Riken and also here. So thank you for your attention.